Thank you for joining this lesson. We're going to discuss Physics Paper 1, Section A, 25 marks. We are told in Part 1 that a measuring cylinder, calibrated in cubic centimeters, water, and a weighing balance were used to find the density of a stone. The arrangement was as shown in the figure 1 below. Therefore, we got a figure 1 here, whereby there is a measuring cylinder having some water inside to a certain level. Then we have a weighing balance here indicating some mass. Then in the next setup, we got the measuring cylinder now when the stone has been immersed inside, and the weighing balance is also showing a new reading. Then we are told to determine the density of the stone. So we're going to use this setup or this experiment to determine the density of the stone. Remember, for density to be obtained, we need mass and volume divided, because density is one of the derived quantities. So for us to get mass of this stone, then we get the final mass in the weighing balance minus the initial mass, because it means the new mass is due to the addition of the stone, because the setup without a stone is reading 0.22 grams, but now with a stone we got 30.22. So we can subtract the 0.22. This is giving us exactly 30 grams, or even 30.00 grams to the accuracy of this weighing balance. After getting the mass, let me go to the next thing, which will be now determining the volume. So volume will still be given by volume 2 minus volume 1 according to the measuring cylinder. We can see initially volume was, because this is 10 and the calibrations are 5 divisions within 10 units, then it means per division there is 2 units. That means this is 10, 10.2, 10.4, 10.6, 10.8, and 20. So it is to mean that just before 10, there was 9.8. Therefore, initial mass was 9.8, initial volume, sorry. Then final volume now is becoming, after 10.8 and before 20, we have 19, because the level is exactly between 10.8, not even 10.8, but because this is a 10, it means there is a 12, 14, 16, 18, then 20. So it's 19, exactly in between there. It's 19. That means the initial here is 0.8, not even 9.8. This is going to be 8 cubic centimeters, because there are 2 divisions. There are 2 units per division. So this is going to be 8. So that we go to 10. This will be 12. So there are 2 divisions, 2 units per division. Now 19 minus 8 will give us 11. Then our density now will be the mass, which is 30 out of 8. So 30 divided by 11, sorry. Divided by 11, I should change this to 11. Divided by 11 is giving us 2.727 grams per cubic centimeter, which is otherwise expressed as 27 kilograms per meter cubed. We usually multiply density by 1,000 when it is in grams per cubic centimeter to make it kilograms per meter cubed. So that is how number 1 should be approached. In number 2, we are told to give a reason why the players draw their ends backwards as the ball is caught in cricket. So for a player to catch a ball in a cricket, they draw their ends backwards. It should be known that we do this, or the players do this, to increase time of impact. To increase time of impact. and hence lower the impulsive force. And hence lower the impulsive force. It should be noted that impulsive force, according to Newton's second law of motion, is usually given by the rate of change of linear momentum. So final momentum minus initial momentum out of the time taken for momentum to reduce from maximum to 0. Now, the faster it takes, then the greater the impulsive force that will be resulting. But the shorter it takes, it means the divisor here will be great and the resulting force is going to be small. Therefore, they increase time of impact. So that resultant force, which is the impulsive force, is lowered. That way, the player will not feel a great force. The same is as the reason why high jumpers, still in athletics, high jumpers will have mattresses on the ground. It is to increase the time of impact so that impulsive force becomes small. That player will not be hurt, as compared to when the ground is very hard and linear momentum will be reducing in a very short time from maximum to minimum. That means resultant force would be greater. So they use matrices to increase time of impact, lowering the time of lowering the impulsive force. Figure 2 shows a lift pump used to draw water from a well. So there is water in a well, there is a lift pump as shown. Now the question that follows is telling us to give one limitation of using this type of a pump. The lift pump has a limitation such that water can only be lifted or raised. Water can be raised from a maximum depth. From a maximum depth of approximately 10 meters. Beyond there, atmospheric pressure cannot pump water upwards. Therefore, this is one of the limitations of such a pump. In part B, a lift pump can lift water to a maximum height of 10 meters. Determine the maximum height to which the pump can raise paraffin. Then the density of paraffin is 800 kilograms per meter cubed. That of water, 1,000 kilograms per meter cubed. And gravity is 10 newtons per kilogram. Therefore, this lift pump is working through the support of what we call atmospheric pressure, and atmospheric pressure can pump a liquid up such that the pressure of the liquid being supported is equivalent to the maximum value of this atmospheric pressure. That means that the value of atmospheric pressure due to atmosphere, is equal to the pressure that it can support due to water. So H rho G will give us the pressure of water. A height of 10, a density of 1,000, and a G of 10 will give us 100,000 Pascal. That is the pressure which can be supported. That means if this is the value of atmospheric pressure, then the same value will be supported as pressure for paraffin. Therefore, we would say that the same pressure for paraffin is going to be a known height of paraffin, and now 800 is the density and 10. This will give us H, and when you divide through, you'll be getting 12.5 meters. This is the height of paraffin that would be supported by atmospheric pressure, or rather, that will be pumped by a lift pump at this same altitude. The next question, figure 3, shows a pith ball inside a transparent flask. When a jet of air is blown over the mouth of the flask as shown, the pith ball is observed to rise from the bottom. This is a pith ball, very light. When you blow air up here, we are told that it will be seen rising from the bottom. Now we are taught to explain the observation. There is a raising up because when air is blown up there, when air is blown at a higher speed at the mouth of the flask, there is reduction of pressure at the same point. There is reduced pressure at the same point. At the same point. There will be reduced pressure at the same point. Now with the reduced pressure, it means the atmospheric pressure below the pith ball now will be greater. The atmospheric pressure below the pith ball being greater because up there it has been reduced. Being greater raises the ball up. Raises the ball up. Then the next question, number 5, is talking of a uniform metal strip of mass 400 grams and length 100 centimeters is placed on a pivot and kept in equilibrium by a force F as shown. So as shown here, we have a uniform metal strip. We've been told it is 400 grams mass and 100 centimeters length. It is pivoted at this point as indicated. Then there is a force keeping it in balance, which is a force F. We are now told to determine the value of F. So for us to know the value of F, we should apply the principle of moments, which is also called the law of lever. When an object is pivoted such that it is not pivoted at the center, then we say its own weight, unless the weight is negligible, its own weight acts through the center. And that weight can be determined from the mass, which is 450 grams. We divide by 1,000 to make it SI units, then times G, because mass times G gives us weight. Therefore, the weight is going to be 4.5 newtons acting through the 50 centimeter mark. And now we are told that 20 centimeters away, if I'm not wrong, let me confirm from the diagram. Yeah, 20 centimeters away, there is the F. There is force F. This is 20 centimeters. Then there is a 15 centimeter here. From 0 to where 20 is, there is 15 centimeters. This is to mean that from 0 to where the pivot is, there is 35 centimeters. 35 centimeters. Therefore now, we can apply the principle of moments, which says that the sum of clockwise moments is equal to the sum of anti-clockwise moments about the same point, given that the system is in equilibrium. Therefore, with equilibrium, now we will say the clockwise moments, which are due to the weight, that will be the force there, and the force is 4.5 times the distance from point of support, which is, because this is 35 and this is at 50 centimeter mark, then the difference in distance now will give us the distance here, and it will be 15 centimeters. So we have to divide by 1,000 by 100 to make it as a units, equals to the force, which is unknown here, times a distance of 20. Therefore, that will give us the value of F, and we will be able to know its value. Therefore, I can now take 4.5 times 20 or times 15, then I divide by 20. This will give us 3.375 newtons. 3.375 newtons. The next question is number 6. The matchsticks are placed, or 2 matchsticks are placed on water in a basin, few centimeters apart as shown in the figure 5 below. We have matchsticks which are a few centimeters away. There is water here. The figure is figure 5. Then we are told to state and explain the observation made when a drop of soap is placed at point X between the matchsticks. So at point X, when you place a soap solution there, it should be known that the matchsticks are resting on the water surface due to what we call surface tension. So there is a force called surface tension making the matchsticks to rest on water surface. But now soap solution, being an impurity, lowers surface tension. So we can say that the matchsticks moves away from one another. Away from one another. Then something else we should note now is the explanation. This is because the soap solution lowers surface tension at point X. Lowers surface tension at X. At point X, surface tension being greater on the other sides, being now greater on the other sides, pulls the matchsticks away. So they'll be pulled away from one another, and this is due to the greater surface tensions now on the opposite sides. Now that between them surface tension becomes too low. We can go to number 7. 3 springs shown in figure 6 are identical and have negligible weights. The extension produced on the system of springs is 25. Then we are told this glass rod here is of weight 1 Newton. This is of weight 1 Newton. Determine the spring constants of each spring. What we should know is that when springs are in a system, like in this case, these two are in parallel, and the resultant spring constant is going to be, because they are only 2 times the spring constant of each. But this one, spring constant is K, because it is just alone. Then now we should be able to know what extension is caused in the first setting here. So for us to get extension, we need force out of spring constant. And the first 2 springs are lifting a load of 20 grams or 20 newtons, and the 1 Newton rod. So 41 out of 2K. Extension 2 for this other case here will be, now the first, the spring here, which is alone, is just lifting 20 newtons, and the spring constant is K, because it is alone, not 2K where they are 2. So now it's this one. So when we add the two extensions, we should get the total extension provided in the question, which is 25 centimeters. So when we take 20 out of K and we add 41 out of 2K, we are supposed to get 0.25. I'm trying to make it as a units. Yeah, 0.25. So we can multiply this by K all through, so that because K, by K. Let me multiply by K by k and by k, so that this part becomes 20 plus 41 out of 2 equals to 0.25, sorry, 0.25k. That means we can take 41 over 2, then we add 20, then we divide by 0.25. This gives me exactly 162. This should be newtons per meter as the spring constant, the value of K. So that is the quickest approach I would advise learners to follow. Express respective extensions, then add them and say that they would be equal to the given extension in the system. We are winding up. In number 8, we are told that figure 7 here shows two identical balloons, A and B, filled with air and their open ends closed tightly. They are closed tightly. They are put at equal distances from a metal tank holding hot water. This is a metal tank holding hot water. Then the sides of the tank facing the balloons are painted differently. So painting differently means that this one is dull and the other surface here is polished white. There is a balloon B, there is a balloon A. It is observed that balloon A expands more than balloon B. Explain this observation. Therefore, this balloon will expand more because it is on the side painted dull, and we should know that dull surfaces are better emitters of thermal radiation. So better thermal emitters are also better absorbers. So dull surfaces, if they were observing, it could have absorbed at a faster rate than the polished one. And now that they are emitting, it also emits faster. So we are saying that dull surfaces are better emitters, of radiant heat, than polished surfaces. Now, them being better emitters, it means heat is being emitted at a faster rate. The first balloon here absorbing it again at a faster rate, hence the greater absorption, or the more expansion. So that is why it absorbs at a faster rate, because it expands at a faster rate because it is absorbing more heat due to the dull black surface. An oil drop of volume spreads on water surface to form a patch of area. Determine the diameter of an oil molecule in the oil drop. Therefore, we usually make an assumption that the oil drop which has been placed on a water surface spreads until there is no oil molecule which is above another one. So after all the spreading has taken place into a patch, it is assumed that the thickness of this patch now is equivalent to the diameter of one oil molecule. And that is why we equate the two volumes. The volume of the drop of oil should be equivalent to the volume of this patch which has been formed. And now that for the patch we are having the surface area, then multiplying it with the thickness here gives us volume. Cross-section area, which is circular, times the thickness should give us volume. Therefore, we will say that thickness, or rather diameter, is given by volume of the drop divided by cross-section area of the circular patch. Therefore, we need a volume of 1.922 times 10 power negative 8. When this is divided by 7.069 times 10 power negative 6. Now we'll be able to get the thickness. We'll be able to get the thickness of one molecule. So let me compute it very fast. 9.922 multiplied by 10 power negative 8. Then I divide this by 7.069 times 10 to the power of negative 2. This is giving me exactly 2.7 times 10 raised to the power of negative 7. This will be meters. So that is the thickness of the one molecule. Figure 10, or number 10, figure 8, shows apparatus used to study Brownian motion using a air-trapped or smoke-trapped in a smoke cell. So we have smoke in a smoke cell. There is a microscope here. There is a glass rod. There is a light of source. State and explain what is observed when looking at the trapped smoke using the microscope. Therefore, when you observe through there, smoke particles are seen in a continuous random motion. A continuous random motion. You're seen in a continuous random motion. Then to explain it, you say this is because the smoke particles are being hit or collided by continuously by air particles which are also in a constant random motion. Which are also in a constant random motion. Therefore, because the air particles in the smoke cells or in the smoke cell are in a constant random motion, they hit the smoke particles, setting them also in a constant random motion. We continue with the question paper. In number 11, figure 9 shows a part of a clinical thermometer. It's labeled K. Name the feature labeled K. Therefore, the feature labeled K, we can say it is the curving here along the glass tube inside a clinical thermometer. That is what we call a constriction. We shall call it a constriction. Then we are told to state the importance of this feature, constriction. It prevents backflow of the thermometric liquid of the mercury, because it is the highly preferred thermometric liquid. So the mercury cannot cannot flow backwards, and that means even later we can have the reading of the patient still being made from the same. Finally, we are told figure 10 shows a passenger bus with luggage compartments under the seats. So under the seats we have luggage compartments, just as seen. This is a luggage bus or passenger bus. The luggage is put under the seats as shown. Explain why bus bodybuilders would prefer to build luggage compartments under the seats rather than on roof racks. So this is to ensure, much weight will be now at the lowest points possible. Therefore, this is to ensure that the position of COG, that the position of the center of gravity, right in full, is as low as possible. Then this increases the stability. This increases the stability of the passenger bus. So the stability of the bus is guaranteed with all the weights or much of the weights at the lowest points possible. Thank you for following. Subscribe and share.